Contactors and relays are both electromechanical switches, but they are used for different purposes and have different characteristics. A relay is an electrically operated switch. It uses a small current to control a larger current. Relays are typically used in control circuits to switch low current loads such as pilot lights, solenoids, and other relays. A contactor is also an electrically controlled switch, but it is designed to handle much larger current loads. Contactors are typically used to control motors, lighting, and heating circuits. The main difference between a contactor and a relay is the amount of current they can handle. Relays are typically rated for currents up to 15 amps or so, while contactors are rated for currents of 20 amps or more, and can go up to hundreds or even thousands of amps. Another difference is that contactors are typically designed to be used in motor control circuits, while relays are not. Contactors have features such as overload protection and short circuit protection that are not typically found in relays. Here's a more detailed breakdown. Firstly, contactors are heavy-duty devices designed for switching high current circuits, typically used for motors, lighting, and heating loads. They are built to withstand the inrush current associated with starting motors, which can be several times the normal running current. Contactors usually have a higher ampacity rating compared to relays. Secondly, relays are generally used for low current applications in control circuits. They are used to switch signals or control other devices. Relays are often found in electronic circuits, PLC programmable logic controllers, and other control systems. Their ampacity rating is usually lower than that of contactors. Thirdly, contactors typically have multiple poles or contacts, allowing them to switch multiple circuits simultaneously. This is common in three-phase motor control applications. Relays can also have multiple poles, but they are more commonly found with fewer poles than contactors. Fourthly, contactors are often equipped with additional features like overload protection, arc suppression, and auxiliary contact. Overload protection helps protect the motor from damage due to excessive current draw. Arc suppression minimizes the arcing that occurs when the contacts open and close, extending the life of the contactor. Auxiliary contacts provide additional control signals for interlocking or monitoring purposes. Fifthly, relays are often smaller in size and more compact compared to contactors. This makes them suitable for applications where space is limited. Contactors, due to their heavy-duty construction and additional features, tend to be larger. Sixthly, consider the voltage levels. Contactors and relays operate at different voltage levels. Contactors are designed to switch high-voltage circuits commonly found in industrial applications such as 480 volts or 600 volts. Relays are often used in lower voltage control circuits such as 24 volts DC or 120 volts AC. Seventhly, the construction differences are notable. Contactors are built with robust materials and heavy-duty contacts to withstand the high currents and mechanical stresses associated with frequent switching. Relays typically have smaller contacts and less robust construction since they are used in lower current applications. Eighthly, consider the operating speed. Relays generally have faster switching speeds compared to contactors. This is because they have smaller contacts and require less force to move them. Contactors, due to their larger size and heavier contacts, have slower switching speeds. Ninthly, in terms of applications, contactors are commonly used in motor starters, HVAC systems, lighting control panels, and other high current applications. Relays are used in control panels, electronic circuits, PLCs, and other low current applications. Tenthly, consider the cost. Relays are generally less expensive than contactors due to their simpler construction and lower current carrying capacity. Contactors, with their heavy-duty construction and additional features, tend to be more expensive. So, in summary, a contactor is like a heavy-duty switch for high-power equipment, while a relay is a smaller switch used for control circuits. Contactors handle large currents and are used to control motors, lighting, and heating, while relays handle smaller currents and are used to control other devices. The specific choice between a contactor and a relay depends on the application requirements, including the voltage, current, and switching frequency. For example, if you need to control a large motor, you would use a contactor. If you need to control a small light, you would use a relay. Consider an example of a motor starter circuit. A motor starter circuit uses a contactor to switch power to a motor. The contactor is controlled by a relay, which is in turn controlled by a push button. When the push button is pressed, the relay energizes, which closes the contacts of the contactor. This allows current to flow to the motor, starting it. When the push button is released, the relay energizes, which opens the contacts of the contactor. This stops the current flow to the motor, stopping it. Another example is in a lighting control panel. A lighting control panel uses contactors to switch power to different lighting circuits. The contactors are controlled by relays, which are in turn controlled by a timer or a light sensor. The timer or light sensor can be programmed to turn the lights on and off at specific times or when the ambient light level reaches a certain point. This helps to save energy by ensuring that the lights are only on when they are needed. It is important to select the appropriate contactor or relay for the specific application. Using a contactor or relay that is not rated for the voltage and current of the circuit can be dangerous and can lead to equipment failure. Consult the manufacturer's specifications to ensure that the contactor or relay is suitable for the intended use. In addition to the current and voltage ratings, consider the environment in which the contactor or relay will be used. If the contactor or relay will be exposed to moisture, dust, or other contaminants, choose a model that is designed to withstand those conditions. Also, consider the operating temperature range. Some contactors and relays are designed to operate in extreme temperatures, while others are not. When installing a contactor or relay, follow the manufacturer's instructions carefully. Ensure that the wiring is properly sized and that all connections are tight. Also, be sure to provide adequate ventilation to prevent overheating. Regular maintenance is essential for ensuring the reliable operation of contactors and relays. Inspect the contacts periodically for signs of wear or damage. If the contacts are worn or damaged, replace the contactor or relay. Also, check the wiring for loose connections or corrosion. Tighten any loose connections and clean any corroded areas. Consider the National Electrical Code NEC requirements for contactors and relays. The NEC contains specific requirements for the installation and wiring of these devices. Ensure that all installations comply with the applicable NEC requirements. For example, NEC Article 430 covers motors, motor circuits, and controllers. This article provides requirements for the selection and installation of motor starters, including contactors and overload relays. NEC Article 725 covers Class 1, Class 2, and Class 3 remote control, signaling, and power-limited circuits. This article provides requirements for the wiring and protection of control circuits that use relays to switch power to other devices. Understanding these articles helps ensure safe and compliant installations. In summary, contactors and relays are essential components in electrical systems. Understanding their differences, applications, and proper installation is crucial for electrical professionals. By considering the factors mentioned above, you can select and install the appropriate contactor or relay for any given application, ensuring safe and reliable operation. Remember to always consult the manufacturer's specifications and follow the NEC guidelines for safe and compliant installations. This knowledge will help you in your electrical career and ensure you can handle a wide range of control circuit applications.